Hey guys, welcome back to my channel, Physics with Philosophy. Today we're going to be looking forward to some basics of vectors, that's required for like class 11th physics and stuff. Okay, so this is a series I'm going to be discussing about vectors. Then the next video is going to be about differentiation, then integration, and then we'll cover up the whole part of the 11th standard basics that you require for your CBSE 11th grade physics. So the first topic that we're discussing about today is vectors. Now, if you ask a basic question, what are vectors? Vectors are nothing but physical quantities that's used to define the movement of an object in space with the help of the magnitude of the physical quantity as well as the direction. Now, there's a physical quantity known as scalars that's used to describe the movement of an object across space using only magnitude. And for example of that could be, you might have studied in class 9th. If you haven't, then it's totally fine. Just continue watching the video. So for an example of a scalar, we have speed here. Let's take for example, to understand the concept better, about magnitude and direction. Okay, let's say this is a body. Let's say the body is accelerating in this direction with the speed of, or a velocity of 50 kilometers per hour. Okay, 50 kilometers per hour. Or let's take 50 meters per second. Okay, it's moving really fast in this direction. Now the thing is, there's two ways of describing the movement of this body in space. We can say that the body is moving with a speed of 50 meters per second. Then we do not have the idea of velocity. We do not have the idea of direction in which it's moving in. We just know the fact that it's moving 50 meters per second. We don't know what direction, but it's moving. It's moving at a speed of 50 meters per second. That is what a scalar quantity is. That is how far a scalar description of an object can tell us about its movement. Okay, now to study it better, we need to understand, or we need to know, or we need to identify the direction in which this body is moving. Because if the body is moving like this, or if the body is moving in this way, or if the body is moving this way, it would definitely affect with our observations. Let's say we are trying to study the collision of this body. Let's say we are trying to study the collision. If the scientist says that, okay, this thing is moving 50 meters per second, okay, that's just limited information. We do not know in which direction this body is moving in. Let's say the scientist's objective is to collide these two particles, but then the only information that is given by the particle physicist is that the body is moving at a speed of 50 meters per second. Then the scientist wouldn't know if it's going to hit this particle, or if it's moving in this direction or this direction or this direction. So to study it better, we bring out the concept of magnitude with direction. Okay, now let's put this particle here, magnitude with direction. Let's say it's moving 50 meters per second, and we want these two particles to collide. So we'll make it move in this direction. Now the scientist has enough information to actually process the data and to come to a conclusion, or to carry out an experiment. And now, how do we define this direction with magnitude? We can say that the body is moving 50 meters per second in the direction of x-axis. So now we identify the magnitude of the body, or magnitude of velocity, or which is nothing but speed, along with its direction. Now this is nothing but a vector quantity, and this vector quantity where speed has a direction is called velocity. Velocity is a vector quantity. Okay, so now this is the basic idea behind vectors that I just explained with the help of an example. I hope you got the idea of it. And an example of a vector could be velocity, displacement, and more examples of scalar quantities could be speed, distance, time, etc., where you don't identify with like the direction. How distance? Let's take 2 points. Let's say this is 50 meters, this is 75 meters, and this is 100 meters. These are the different paths that a person takes to travel from these two points. Okay, now in space. Now if we talk about the displacement is, it never changes. It depends on the direction. Let's take, this is the direction. It's the direction along with the magnitude. So this is the displacement. Displacement is nothing but the shortest distance between 2 points, whereas this distance is the total path traveled by the body. So distance doesn't depend on direction. It does not matter if the boy has traveled from A to B in this direction, doesn't matter. It just only cares about the magnitude. Whereas displacement actually matters because it's the shortest distance between any 2 points. So I hope you were able to get a basic idea of vectors from this. Now we're going to be looking forward to more in depth about vectors. So we'll just erase these things here and we'll look at vectors in detail. Now we are going looking forward to the representation of vectors. Okay, now we have talked about the vector quantity, velocity, just a moment ago, and the scalar quantity speed. Now let's draw a small comparison between it. What is velocity? Velocity is nothing but displacement per unit time. Speed is nothing but distance per unit time. Distance is scalar, displacement is vector quantity. But now we are going to be looking for the representation of vectors. We represent velocity with the variable or with the alphabet V, with an arrow sign in the top that indicates the direction along with the magnitude. Okay, so this is how we represent a vector quantity. If we have a vector, let's say a person says, okay, we have a vector A in this direction. How do we represent A? We do not just write A in this way. We do not just write A like this. We write A with this thing. So what do we call it? We call it A vector. That's what we call it as. Okay, now moving to the next concept. What about speed? How do we represent speed as? Speed we represent just with the letter S, or it could be just V, magnitude of velocity. Now what is this that I just brought it up on the screen? This is nothing but to see velocity vector is nothing but speed with direction. Now if we want to talk about only the speed and we want to neglect the fact that it has a direction, then we talk about the magnitude of velocity. We do not want to include the direction. Now how do we represent the magnitude of velocity? By drawing a mod and placing the velocity vector inside. So for example, we could say that the velocity vector is 5 meters per second in the direction of x-axis, But then if we talk about what is the magnitude of this velocity vector, then we represent it like this, and the magnitude is nothing but 5 meters per second. This is the basic idea. Now that we have this cleared, we'll talk about we'll talk about unit vectors now. That's another topic that comes under vectors, unit vectors. Right now we just looked at a way to represent vectors, which is moving in a certain direction. Let's say this is a vector, a velocity vector, or let's say it's a force vector. You're applying force in this direction, okay? Then we can say that a force of, let's say, 10 newtons is being applied in the direction of x-axis, But you see it's a long process. Like we have to write all of this stuff, and when you advance later on in physics and stuff, for scientists they found it difficult to describe every single physical quantity in such a lengthy manner. So they decided to shorten it, and the way they shortened it was not in this way. They did not call it 10 Newton X. No, this is not how they called it. But then there was another way to to convey the message that was described here within a small single letter, and that letter was or is I cap. Now I'll explain what this is. Okay, now scientists just want to find out if they were lazy, so they didn't want to write this whole thing, so they wanted to figure out a smaller way to represent the whole the whole statement here, but then without the effort of writing the whole thing down. So they brought out 3 variables. Okay, now what are these 3 variables? These 3 variables are I, J, and K. Okay, and then the thing is, when they're called unit vectors, we represent it by a small cap in the top. So we call it I cap, K cap, J cap, or I cap, J cap, and K cap. Now why did the scientists bring out this value? We'll be looking forward to the meaning of it. What does I cap mean? I cap mean a unit vector in the direction of x-axis, x-axis. Now what does J cap mean? J cap means a unit vector in the direction of y-axis. And now what does K cap mean? A unit vector in the direction of z-axis. So now rather than writing this whole sentence to describe the magnitude and the direction of a physical quantity, of a vector quantity, we have a single letter that represents the whole meaning of what we have. And now let's look forward to a way in which we can some examples. Okay, like for example, this force vector itself. Now we can say, for example, let's take let's say a car. Okay, a car is moving, a car is moving in this direction. Now a car is moving in this direction. Now can you guess, is it moving in the x-axis or is it moving in the y-axis? Obviously not in the z-axis, because we're talking about 2D objects here. Okay, so we'll neglect the z-axis for time being right now. And now answer this question: is it moving in the x-axis or in the y-axis? And how would a scientist describe the motion of this car without the help of unit vectors? Okay, sorry, what we call these things are unit vectors, by the way. I cap, j cap, and k cap are unit vectors. Okay, so now getting back to the topic, how would a scientist describe the motion of this car? A scientist could possibly say that the car is moving in a direction that's diagonal to a potential rectangle that could be drawn here, or something like that. But then it becomes too complicated, right? So what we do is we break down this vector in both x-axis and z-axis, because when you think about it, the car is supposedly accelerating in both x-axis as well as y-axis to move in this direction, So in that sense, we can break this vector down in two components, in the x-axis component and the y-axis component. A scientist could say that the car is accelerating in some part in the x-axis and some part in the y-axis, which causes its movement to be, overall in this direction. Now, how do we represent it in the form of vectors? We could say that, the velocity is nothing but, a unit vector in the x-axis. So let's say, vx, there's a unit vector in the x-axis. Now what is a unit vector that moves along the direction of x-axis? It's I cap plus a unit vector y-axis, which is represented by j cap. Now these values could be anything. These values could be anything. These values could be anything. It could be 5, it could be 50, it could be whatever. It depends on the observation. So this is a method to represent, this is a method to represent a vector using the help of unit vectors. Now we're going to be looking forward to this in more detail. Hold on. Yeah. Unit vectors itself. Okay. I'm going to make you visualize this concept of unit vectors in a much more detailed sense. Okay. I cap, j cap, and k cap. We can imagine, let's say you are a person, okay? You are a person, you're standing here, and your friend is also standing here, okay? Let's say he has this hairstyle, you have this hairstyle. Now there's a box, okay? There's a box, okay? There's a box. Now this person is pulling this box towards him with the force of 5 newtons, and you're pulling it to yourself. You're like, no, I want this box, and you're pulling it with a force of 10 newtons. You're stronger than your friend, okay? Now, where do you think this box would move? Like, what direction would be the potential direction of this box, as a resultant force caused by both you and your friend? We all know the answer to this question. It would obviously move in this direction, right? The box would move in this direction if you're pulling it like this and your friend is pulling it like this. So now, if we look at the form of theory, if we look at it from a mathematical perspective, like let's say a scientist is trying to study this whole, the scientist is trying to study this whole sequence of events that just happened here, then he would draw, basically nothing but two vectors like this. He would give it a magnitude of 5 newtons. This would have a magnitude of 10 newtons. And he doesn't have to mention the direction. He doesn't have to mention j cap or something like that, because he has already described the direction of it. He has already described the direction of it with the help of an arrow mark. So he has it visualized like this. And then the resultant of these two vectors comes out to be in this direction. Now what the scientist intends to do is that he wants to find out what this resultant vector's potential, description mathematically would be. Like, let's call this vector as vector resultant. He wants to figure out what this resultant vector is, whatever it would be, what is the overall net force that's being applied on this box as it moves in this direction. So we can't say 10 plus 5. We can't say 10 plus 5. We can say 10 plus 5 if the box is being pushed in the same direction. If there's a 5 Newton force being applied in this direction plus another 10 Newton force being applied in this direction, then we can say that the overall vector magnitude of this force would be 5 plus 10. But then here it's different. We can't do the normal addition that goes around. So we have to talk about resultant quantity. And how do we represent a vector like this? We we do the same thing that we just did in the previous, slide, or not not slide, but then you get the idea. We talk about how much force is being applied in this direction, which is nothing but 5. But then what is this direction? I cap plus 10 j cap. Now this is the resultant vector force. Okay, let's just put this out, and this is the resultant force that's being applied in the box, which if we measure this force, we'll get this vector quantity. Now you'll be talking about, okay, we are measuring the force that's being applied on the box as it moves in this direction, yeah? What's the force that's causing the box to move in this direction, yeah? But then if you talk about magnitude itself, how do we find the magnitude of this vector? How do we find the magnitude of because see, this is nothing but we're just talking about directions, but what about the magnitude? Well, some scientists, we are thankful, some scientists and mathematicians have together, described a formula, a basic formula to talk about the magnitude of a vector quantity, of any vector quantity that has unit vector that is described with the help of unit vectors. And what is the formula? The formula is resultant vector magnitude, or any vector. Okay, any vector's magnitude is given by the formula the whole root of x naught square plus y. I'll explain this in a second. Plus z naught square. Now what is this? This is nothing but the magnitude. This is nothing but the magnitude of the vector in x-axis, which is nothing but the coefficient of this unit vector. Whatever is written next to the unit vector, this becomes the x naught. Okay, this becomes the x naught. And whatever is written next to the unit vector of j cap, or unit vector of y-axis, becomes y naught. So this is just a way to represent the magnitude, magnitude of the vector in a specific direction, x or y. This is nothing but magnitude in x-axis, magnitude of vector in x-axis, and similarly for y and z. So here, what is the magnitude of this resultant force? We can say that the magnitude of the resultant force is nothing but 5 square plus 10 square, which is nothing but, what is 5 square? 25 plus 10 square, 100. We have 125 root. You can calculate the root and find out the force. So this is the overall force, or the net force, that's being applied on this body, on this box, when you both pull on it from these two directions. Now that we have this basic idea about unit vectors and stuff, we can talk about another concept, like a way to represent vectors. Vectors is nothing but we know that it's given by both magnitude, which is represented like this, and the unit vector cap, which is represented by cap. Now sometimes in question you'll get they will ask you to measure out just the unit vector. What is the unit vector? Okay, in a second we're going to be looking forward to in more detail about unit vectors, but then just listen here. Okay, now if a question asks you to find out what the unit vectors are, what you do is you just substitute. Not substitute, you just transpose. Not transpose, but then you just switch the the quantities here. You have vector divided by the magnitude of the vector. Then you'll get the unit vector. This is a formula that you can just keep in your mind. How? A vector is nothing but described by magnitude and then its direction. What is the magnitude? Magnitude is given by the mod around the vector itself, and then the direction is given by the unit vector. Unit vector I cap, j cap, or k cap. Okay. And then you have this equation, and from this equation comes another equation using which you can measure out the value of the unit vector. Now let's look forward to unit vectors. Let's look forward to what unit vectors are. Let's take a random vector in a Cartesian plane. Okay, let's take, this is a vector. Let's say that this is a vector. Okay, this is a vector. Now what is a unit vector? Unit vector is nothing but a vector. Let's say the unit vector is the vector v like this. Okay, vector v like this. Okay, so we have this unit vector. Unit vector is nothing but a vector. Unit vector is nothing but a vector which magnitude, whose magnitude is nothing but 1. Okay, I'll repeat, sorry. A unit vector is nothing but a vector with magnitude 1. So here we have, let's say here we have, for example, we have a vector v whose magnitude is not equal to 1, But then if we try to find out a small part of it, a small vector part of it, if this is vector v, then this could be, v cap. Now what is this v cap? V cap is nothing but if we try to find the magnitude of v cap, then we'll get 1, and v cap is a part of the large or the main vector v. So what do we mean when we're talking about unit vector along x-axis and unit vector along y-axis? We're talking about nothing but a vector that is along x-axis whose magnitude is 1. We're talking about a vector along x-axis whose magnitude is 1, and the way to represent this is by I cap. Similarly, a unit vector along y-axis is nothing but a vector that is along the direction of y-axis whose magnitude is 1. So if somebody asks you what is the magnitude of j cap, then you just say 1. Same goes for z-axis as well. K cap magnitude is 1, but k cap is a unit vector. So that's the idea of unit vectors. And why do we bring out this concept of unit vectors? So that we can better describe the motion of an object which is so random. Let's say an object is here, let's say an object moves from here to here, okay, and it's 3D. So we can imagine, if we draw about the, like the projection of it in 3D, you can just imagine. So it has some component in y-axis, okay, it has some component in y-axis, it has some component in x-axis as well, it has some component in y-axis, this is z-axis, yeah, it has some component in y-axis as well. So the thing is y, x and z. The thing is, to better understand this motion of this body, we use unit vectors because their magnitude is 1, so it's easier to calculate and understand and describe the motion of such a body. That is why we brought out the concept of unit vectors. So this is all for the basics of vectors. Now we have concepts like components of vectors. Now what is a component of vector? Vector componentiation. We componentiate vectors. Componentiate vectors. Now we're going to be talking about this topic. Now what is this topic? Componentiation of vectors. See, listen, what does a component mean? Like we can say that, let's say we have water. What is a component of water? H2O is a component of water, something like that, okay? Or we can talk about another example of what a component means. Let's talk about a car, okay? A car. Wheel, we can say that wheel is a component of car, or in other words, wheel is a part of this car. So by componentiation, we mean that we are breaking down the vectors into different parts so that we can understand the main vector in a much detailed sense. We literally did that with the force example. We talked about how you and your friend were pulling this box in these 2 directions. And as a result, a vector was forming here, right? As a resultant force, a vector was forming here. Now, what is this? What are these 2 vectors? These 2 vectors are nothing but the components or the parts of this main vector that's being formed here, which is the resultant vector. Now, if we reverse this idea to break down a vector rather than forming a vector from 2 components, let's talk about breaking down a vector. Let's say we are given a vector like this in this direction. Now, how do we define this vector? It's not like we can change the position of this vector and describe it as something that's moving along in the direction of x-axis. That's not possible, right? We need to describe the vector as it is. We know that this is x-axis, this is y-axis. What is this axis then? We don't have any idea, but then we can then understand or study this vector by breaking down into two components. How do we do that? Let's look at that. Let's draw a Cartesian plane first. Okay, let's draw a Cartesian plane first. We can, this x-axis, this y-axis. Now we can break down this vector into two components. We can think about it in such a way, like let's say that this vector is a force vector. We can say that, force vector. We can say that a force in this direction is potentially occurring due to some force in this direction and some force in this direction, and as a result this force is occurring. Okay, so this is how we break down a vector, any vector. The best way to visualize a vector is through either force or best way is to visualize it through force whenever you get a vector. So you first break it down into two components: the component in the direction of x-axis like this, and the component of y in the direction of y-axis, which is the component of y. Okay, so now this is a whole different equation on its own. What do we have here? We have, let's say there's an angle theta as well, in which this force vector is being projected. Okay, so we have nothing but the main vector force and its two components in the direction of x-axis, in the direction of y-axis. So we can talk about it being fx and fy, and the resultant force f net means resultant, net force, like that, resultant force. And there's an angle theta that makes with the x-axis. Now if we look at this, we can see the vectors that we're studying about are all free vectors. Yeah, so we can actually move the position of this vector over here and then try to study it in a much better way. Now how do we do that? What do we have here? We have these two vectors, and then as a result this vector is being formed. Okay, so how do we the objective now we are trying to look for is what are the values of these two components due to which the overall force is being caused. How do we do that? Here we try to take let's talk about the horizontal component of the net force. So these are two vectors that we have this side and this side. Okay, now if you look at the triangle, you might have studied trigonometry in class 10th. Okay, you might have studied trigonometry in class 10th. A trigonometric ratio that's associated with the base and hypotenuse. What is it? It's cos theta, right? So if you try to take cos theta of this triangle right here, we would have this component, which is nothing but fx component. Let's say it's the x component. Okay, x component of force. So the x component of force divided by the hypotenuse, which is nothing but the overall force. And what are we talking about here? We're not talking about vectors, we're talking about the magnitudes. We're talking about their magnitudes. So now if we just move the position of f net here, we have the value of the x component of the net force, which is nothing but x component, or let's just call it x component. X component equals f cos theta. Net. We can also just represent it without the arrow mark to show the magnitude. F cos theta is equal to the x component. We can say the x component is fx with magnitude, or if we don't want to lengthen out the whole process, you can just ignore this vector and then we don't need the magnitude sign. So yeah, this is for the x component of the total force. Now if you look at the y component, now we have this figured out. Yeah, you have this figured out. Now we want to figure out the y one. Now what is the trigonometric ratio that's associated with was associated with the perpendicular and the hypotenuse. Obviously it's sine, you would have guessed. So what's the sine theta here? What's the sine theta here? Sine theta is nothing but F y, which is the y component of the force. Or to represent it better, we don't use the arrow mark. To represent it as a scalar, okay, not as a vector, we use arrow, we remove the arrow mark, divided by the magnitude of force, which is the hypotenuse, right, which is F net. Now if we move F net here, we have the y component of the net force, which is nothing but y component is nothing but F net sine theta, which is nothing but sorry, Fy is equal to F net sine theta, or F sine theta, which is the y component. So now if we look at the same vector, we have, let's recall what we just did. We just took a vector F and we broke it down into its two components, okay, two components, not in its vector form, because the vector form is easy to define it by. We can use I cap and j cap to define it by, but then we need its magnitude. Yeah, so we broke it down into its two parts, this whole vector, into its x component and y component. X component's magnitude is given by F cos theta. And now what is F? F is the magnitude of this vector. If we talk about the magnitude of this vector, it's nothing but F. Okay, yeah. And then this the vertical component magnitude is given by F sine theta. Time for examples, because I'm pretty sure most of you would have lost it. So let's look for an example. Let's say there's an object that's moving with a velocity with a net velocity of 10 meters per second. This is a vector quantity, okay? This is a vector quantity. So let's say that the velocity is given by 10 I cap plus 2 j cap. Now what does this mean? How do we study this vector in a much better way? We study this vector in a much better way by breaking it down into its two components, x component and its y component. Mind you, these are both perpendicular to each other. So what is the x component? X component, let's represent by Vx, and y component by Vy. If you want to show the direction, then obviously this thing, but then you don't need it. Okay. So now how do we break this vector down? We can say that Vx is 10 I cap and Vy is 2 j cap. We understood it by the question. Now sometimes in the question these values won't be given, and only the magnitude of this main vector would be given. Magnitude of this vector would be given. Let's say the magnitude of this vector is let's say 50 meters per second, which is the magnitude of this main vector. Now you can't tell what the magnitude of these vector components would be as you're studying this vector. Yeah, you can't talk about the magnitude, but then we just derived a formula for finding the magnitude of the components of the main vector. And what is the formula for the x component one? It is nothing but V, or the main vector, or the resultant vector, or this whatever vector is here whose components we are breaking down, which is V here in this case. V is also 50 meters per second. V cos theta. For the sake of this question, let's take theta to be 45 degrees, or let's take it to be 90 degrees, because cos 90 is 0. Oh, no. Let's take 30 degrees. No, 30 degrees. Nah, let's take 45 degrees. Okay. Now we have a theta of 45 degrees. We have this equation. Now we just have to substitute the values. What is V? V is nothing but 50 into cos theta. What is cos 45? 0, 1 by 2, 1 by root 2. 50 into 1 by root 2, which is nothing but 50 divided by root 2. If you want, you can rationalize this, but then this is the amount of velocity that's that this object, that this whatever this body is moving in is traveling in the x-axis. Now if you look at the y component, we have y part of the main vector. We have v sine theta. What is v? V is not 50 sine of 45 is nothing but 1 by root 2. This is the same value as this one as well. So we know that these two values are obviously, this value is obviously lesser than 50, which is the main one. So we can say that it's the addition of these two vectors which is causing the movement to be in this direction, which can be defined with the help of a vector whose magnitude is 50 meters per second. So now we just talked a bit about the addition of vectors. Yeah, so we can actually talk about how do we add any two vectors. Wow, this is so much stuff. Okay, we can talk about addition of any two vectors. We just talked about componentiating vectors. Now let's look forward to adding any two vectors. So there's two ways. I'm going to be going through this quickly. There's two ways to add any two vectors. First is the triangle law of vector addition, and then there is the parallelogram law of vector addition. Now what we're going to be looking forward to these two in detail. We're going to be looking forward to let's say we have two vectors like this. We have two vectors, one vector is in this direction and this in this direction. How do we add these two vectors? We know that the resultant would obviously be in this direction, yeah? So how do we add these two vectors? What we do is, these are free vectors. Free vectors can be placed anywhere. So we place it here and then draw. Sorry. Why? Okay, sorry. I'll explain why we place it here, okay? We can also, you'll be thinking, why didn't we just place it here, or why didn't we just place it like here or something like that. The thing is, the triangle law of vector addition states that you need to place the head of a vector to the tail of another one, and then draw a third vector to the head of the third one, and then you have this vector, which is nothing but the addition of these two vectors. If this vector is a vector and this vector is b vector, then this vector is nothing but the addition of a and b. If you look at another example, let's take two vectors like this. Then you want to find the addition of, let's say a vector and this is b vector. The question says you to find what is b vector plus a vector. Then what you do is you move this vector, a vector, it's b, right? So b comes first. Since b comes first, you need to put the head of b vector to the tail of a vector, and then draw the third vector. This vector would give the sum. Now the triangle law of vector addition states that if you have a vector, let's say this is a vector, okay? If you have two vectors like this, or let's say you have two vectors like this. Triangle law of vector addition states that you draw parallelogram law of vector addition states that you draw a parallelogram and then you join the diagonal of the parallelogram, and this will give you the sum of these two vectors. If this vector is a vector, this vector is b vector, then this diagonal would give you the sum of a plus b. These are two laws of adding any two vectors. There's derivations and stuff that you can go onto YouTube and try to figure out, because mostly I don't think it will come for CBSE exams, but then just knowing about it is gonna help you with the maths. That's gonna come out later on, but then it's not that needed, to be honest. So now that we look forward to how to add two vectors, there's another topic which is called the product of two vectors. How do we multiply any two vectors? Let's say we have a vector v vector which is 5 I cap. We can multiply it by 2, then we have 10 I cap. But then let's say we are trying to multiply two vectors, okay? What we just did was multiplying this vector with a scalar. We can say that let's say this is nothing but v vector. Then we have 10 v vector, which is nothing but this 5 I cap into 10, which is 50 I cap, which could be 50 times larger. So this is nothing but multiplying a vector with a scalar. It's basic concepts. But then how do we multiply a vector with vector 1 with another vector? How do we do that? We have two methods to multiply two vectors, because vectors are not like normal numbers. So for the first method is dot product, and the second one is cross product. Cross product is kind of complicated. Dot product is pretty simple. You will need cross product for chapters work, energy, power, and dot product for most of the chapters. So here dot product is given by, let's take any two vectors. If you have this vector a and this vector b, the dot product, how do you multiply these two vectors? The dot product is given by a dot b is nothing but the magnitude of a vector multiplied by the magnitude of b vector into cos theta. For example, if a vector is nothing but, let's say 5 magnitude and b vector's magnitude is 6, then we have, what is a dot b? We have 5 into 6, which is nothing but 5 into 6 into, let's say this theta is 45 degrees. 45 degrees. Then we have cos theta, which is cos 45 degrees. Cos 45 degrees is nothing but 1 by root 2. Then we have 30 by root 2, which is the product, which is the dot product. Now what is this dot product used for? Dot product is used to describe how much of a vector, let's say how much of this a vector has a component in b. How much of the vector a has a component in b. It talks about the horizontal components or the horizontal parts of a vector. So it talks about this basically, like a dot b means nothing but this. Some part of a and b. This is what it means. Now what does b dot a mean? What does b dot a mean? B dot a means nothing but we have a vector, then we have some part of b vector. B vector, some part of a vector. No, not some part, main a vector and then some part of b vector. Now what is this thing? See, look, we have a dot b is nothing but a vector's magnitude into b cos theta. And we just looked at what b cos theta is, right? Anything cos theta, a vector, let's say a vector v. What's its horizontal component? Horizontal component is nothing but b cos theta. Here, then what would b cos theta be? It would be the horizontal component of b vector. B vector का horizontal component होगा. So a dot b is nothing but a vector a's magnitude multiplied by the magnitude of b vector whose part of lies in the horizontal direction. That's what it is. You can visualize it in this way. Now if we have this thing, what is this thing? This is nothing but b dot a. B dot a is nothing but magnitude of b. We just talked about how we represent magnitudes, right? b a cos theta. It could be like this. These two are different. So a cos theta is a part of a in the horizontal direction multiplied by b. That's all it is. Yeah. So that's all that's there for dot product. Now we have cross product, which deals with the perpendicular parts of vectors. So what is a cross product between two vectors? Let's say we have two vectors a and b. The cross product of these two vectors will be defined by a cross b, which is nothing but magnitude of a into magnitude of b sine theta. In 12th you'll learn another formula which includes n cap, but then right now we don't need it. This is a formula for cross product. So if we have two vectors like this, we have a and we have b. What's the cross product? Okay, sorry. Let's tilt a bit so that we have theta. What is a cross b? It's gonna be a b sine theta. If the question is asking for b cross a, then it is b a sine theta. And mind you, a cross b is not equal to b cross a. The same cannot be said here though. Now there's more into this concepts, okay, that's involving, like for example, if we have a vector, let's say a vector v, which is nothing but 5 I cap plus 6 j cap, another vector, let's say v2, there is 6 I cap plus 10 j cap. Now we are asking what is v1 dot v2. How do we do it? We do not have theta. And then this formula revolves around theta. We do not have theta, then how do we do it? We do it by simply dot product involves multiplying the coefficients to each other, but we also multiply the vectors, the unit vectors. Now I want to answer one thing. What is I vector? Let's say these are two unit vectors, right? So I vector dot I vector, what would it be according to this formula? It would be I cos 0, because I cap is nothing but something that lies in the x-axis. Both of them are in the x-axis, so the angle between them would be 0. So I cos theta, which is nothing but magnitude of I, which is nothing but 1 into cos 0, which is nothing but 1 as well. So it will be 1. So if we are multiplying these two parts, we have 5 into 6 I into I, which is nothing but 30 into 1. Similarly, we have 5 into 10. We have 5 into 10 into I into j. Now let's see how to do I into j. What is the angle between I and j? Theta would be 90, because I is in this direction, j is in this direction. So what is cos 90? It's nothing but 0. So I dot j would be I magnitude j magnitude cos 90. So it doesn't matter what these magnitudes are, it's both 1 1, but then cos 90 is 0, so it becomes 0. So then this whole quantity becomes 0. That's why there's a trick that involves in multiplying two vectors whose angle between is not given, but then their only vector parts are given. What's the trick? The trick is to simply multiply the same unit vectors coefficients, and then to remove the unit vectors. Okay, for example, I'll explain. How do we do it? I'll explain. v1 dot v2 is nothing but, what did I just say? Multiply the multiply the magnitudes with the same unit vectors, which is 5 into 6, which is 30. We just found out that I into I is nothing but 1, so we don't have to multiply 1. We can actually do it, multiply by 1, plus 6 into 10, which is 60. J into j is nothing but 1. So we have 30 plus 60, which is 90. That is v1 dot v2. Now if we want to talk about the cross product of these two vectors, then it gets a bit complicated, not gonna lie. But we'll talk about it. If we have v1 cross v2, we don't have the angle between these two vectors, but we only have the vectors in its vector form. Then how do we do it? We do not multiply it like how we did in dot product, but then we implement a concept that you learn in mathematics in class 12th in more detail, which is coming from the concept of determinants. What you do is you create a determinant, you place I, j, k cap over here, and then you place the values of each inside. So the values of vector 1 we put it here, values of vector 2 we put it here. What is the values of vector 1? 5, j cap 6 and 10. Both does not have values in the z-axis, so it'll go 0. And in class 12 you'll learn a method to how to solve a determinant. I'll just show it to you once. Maybe you can watch a separate video on determinants later on, or if you want a video on determinants, just let me know in the comment section below and I'll just show it to you in 5 minutes or 10 minutes. Okay, right now I can't do it because the video's length is going to be quite too long. So now that we have this determinant, we'll just go forward to solving it. The method of solving a determinant is plus for this one, minus, plus. Keep it in mind. Now we first cross out like this and we multiply these two with the minus of these two. What is this? Before that, what we do is we first multiplied with this one, which is nothing but I cap into 6 into 0. 6 into 0 minus 10 into 0. Not plus, because see here it's minus. So this whole quantity is plus, minus, minus. Now we cut these two and we remove this one. So we have j cap multiplied by the whole of, what do we have, 5 into 0. 5 into 0 minus 6 into 0. 6 into 0. Now we have plus k cap. Now we remove this and we cut these two parts. Plus k cap. Most of you would know this method already, but I'll still explain. I'll listen to all comments. 5 into 10. Let's just do it directly. 5 into 10 minus 6 into 6. 36. This is nothing but 24, right? So this is 24 k cap plus this is 0. This is also 0. So 24 k cap is the overall cross product answer of of V1 cross V2. What is it? 24 k cap. What's the magnitude? I just talked about in the starting one. X component is not existent, so 0 square plus y component not existent plus z component is existent, 24 square. So it will be nothing but 24 itself. So that is V1 cross V2. This is the method, the determinants matrices method. This is all about vectors, multiplication and stuff. So it's been 52 minutes. I've talked about so many concepts that involves in vectors that you'll require for your class 11th physics, some basics. If there's any section or a topic that I failed to explain it properly enough, just let me know in the comment section below. I'll make a separate video on it in a much more detailed sense with examples and stuff, so that it'll help you guys to master the concepts in a much more great sense. Now that if you've watched this video so far, you can go onto YouTube or open up a book or something and search up some questions that's related to vectors and stuff, some basic questions, so that you can further gain a stronger understanding of the concepts that you have regarding this topic, which will help you to score well for your class 11 physics parts. So yeah, thank you for watching this video. I hope it was able to be of some help to you. The next video that's going to be coming up is going to be on differentiation, and then it's going to be on integration. If I have time, I'll make 2 in 1, but then I don't think it's possible. It's been 53 minutes. I've tried to cover a large part of vectors in such a small amount of time. I hope this video was of help to you. Thanks for watching. See you in another one. Bye bye. Physics with Philosophy. Bye, Liritaji signing out.